So last time we started this new topic on Posets. So we have not yet defined what a Poset is, but we have defined all other axioms, properties of sets or properties of relations. And we studied equivalence relations. Any questions till now? So what we showed is that equivalence relation on a set S, so obviously relation S to S, S to itself, it is nothing but a partition of the set. And one side we have shown equivalence relation partitions the set S into classes, and the other side is, what is the proof of this? If I give you a partition of S, how do you define an equivalence relation respecting this? So say S is S1, S2, SC. This is a partition, which means SIs are disjoint. So the relation will be two elements are related if they are in the same part. So define A, B in R if A and B are in SI for some I. Okay, so two elements are related if they are in the same part. It can be any of these C parts, and otherwise they are unrelated. So you can see that this defines an equivalence relation because it's reflexive, symmetric, and transitive. Is that clear? Okay, so another example is suppose there is we are looking at a square, color the vertices red or blue. There are 4 vertices, so there are 2⁴ choices. That is your domain. Okay, the ways, the number of ways you can color this square, and two colors are related. Two colorings are related if second can be obtained from the first, by natural relations, which means rotation, reflection, or the combination of that, rotation then reflection. So you rotate the square or you reflect, which means you reflect along the median of the square. There are two ways, or you use rotation and then reflection. Okay, so can you show that this relation is an equivalence relation? A coloring is related to itself trivially, so it's reflexive, it's symmetric. Is it symmetric? So you rotate, reflect, you get to another color. How do you go back? You have to rotate first, right? Can you do that? So check that this is an equivalence relation. Question is, what are the classes? So what do you think are the classes? So one is, let's say red, all red. Right, you can color all the vertices red, then you rotate or reflect or whatever you do doesn't change. So this is just one coloring. Suppose you have 3 reds and a blue, then what is there in this class? You can rotate, right? So blue can come in any of the places. Anything else? So that's one class. So this is also called orbit, right? You take an element and you apply all possible transformations. So what you get, these are all related to each other. So that's a class. What is outside these two classes? Is there something else? Yeah, there obviously are more. You can have red, red, black, black, blue, blue. And you can have many of these in the class, in the same class. Beyond this, yeah, the symmetric opposite of this, or RB. Right, and so on. So you can complete this, you can see what the classes are. So the 16 possible colorings, you can see how they partition themselves into classes. How many classes are there, how big are they? And you can check the basic things that they are disjoint, they cover everything and so on. Okay, so we complete this, and now we come to partial order. Any questions till now? So partial order will be like less than equal to, and equivalence was like equality, right? Equivalence kind of mimics equality. Within a class, things are actually considered equal in an equivalence relation. Partial order will be different. So here it's not about equality, but inequality. So now we move to inequalities, and there is a way to abstract out something which will behave like inequality on arbitrary sets. And we will see a very non-trivial result related to Poset. So yeah, even here there will be interesting results. So the definition is, the definition will be very close to equivalence. What do you think you should change? Right, so reflexive and transitive seem correct. It's only the symmetric that you have to change. So you change it to anti-symmetric. If A is less than or equal to B, B is less than or equal to A, then A has to be equal to B. Right, that will give you a feeling like inequalities over real numbers. So relation R is partial order. if it is reflexive, antisymmetric, and transitive. Okay, so this is the only change. Why do you use the term partial? What is partial in this? I think I said this last time that it is possible that there are pairs of elements which are unrelated, right? So this is very different from numbers. In numbers, any two things are related. I mean, there is an inequality you can write down. That may not be true when you abstract to partial orders or posets. So if there is a way to compare any two elements, it's called total order. Partial order R is called total order if for every pair of elements in the domain, which we are assuming to be S, like before, either ST is in R or TS is. And if both are, then they have to be the same. Yeah, so total order means that for any pair, exactly one of these pairs, ST or TS, is present. So these are the definitions. So what are the examples? So the motivational example is, of course, over integers or over reals, less than equal to is partial order, is total order. Okay, by this notation I mean the domain is R, the set of real numbers, and the relationship is the obvious less than equal to. This is a total order. Similarly, okay, what about R less than? Is this an order? Why not? Are you sure? A less than B? Well, just so the problem will be in reflexive already actually. You cannot say A less than A, so this is not. So we are actually abstracting out then less than equal to and not less than. What about R greater than equal to? Yeah, that's also correct. So less than equal to or greater than equal to, both are total orders. What about over complex if you use less than equal to? Why not? Yeah, so it is clearly not total order because you cannot really compare you can't compare I minus I, where this is square root of minus 1. Or anything actually, 0 and square root of minus 1, for example. You cannot say anything about these two. Although 0 seems so small than square root minus 1, you can't faithfully say that 0 is less than equal to square root of minus 1, right? So both of them, this or its reverse, they are not incomparable. Is that clear? So this is not total. Is it partial order? Yeah, it is partial, of course, because sometimes you can compare. So this is partial order. Right, so our definition makes sense because there are total orders, there are partial orders, there are partial orders which are not total orders, right? So you need all these terms. They are non redundant. Third example, what about power set of 1 to n? How do you compare two sets? Subset, right? So containment. And what is this relation? Yes, because you cannot compare, so this is again not total. Correct. Not total as you can't compare 1 with 2. So this is again 1 and 2 are incomparable. And neither is 1 contained in 2 nor is 2 contained in 1. But sometimes you can compare, so it's partial order. And importantly, it is reflexive. So A can be compared with A, anti-symmetric, right? A contained in B, B contained in A, then they better be equal. And transitive, again clear. So this is a partial order. So our notation will be as follows. Since less than equal to is so nice, we'll continue with this more suggestive notation. So partial order will be on S is denoted by S less than equal to. Okay, as I have been doing already, but we can, instead of the subset notation, it also makes sense to use less than equal to with the understanding that it signifies containment. And the other notation will be what is less than. How should you define less than when the relation is less than equal to? So yeah, so A less than equal to B should denote that A is less than equal to B and A is different from B in S. No, equal to comes with the set always. Containment and equal to is well defined. I mean, there is no other option for equal to. But for less than equal to, there are many options. Right? For example, in the case of complex, I said less than equal to use the same notion as reals, but you can also use less than equal to on the norm. So you say that two real numbers like 0 and square root of -1, take the norm and then compare. So it's 0 and 1. Right? So in that sense, 0 is less than equal to square root of -1. So a set affords many partial orders or less than equal to, but a set affords a unique equality. So that we don't need to define that. But we do need to define less than because it critically depends on what is less than equal to. So this is the definition. Any questions at this point? This is just, till now we have only set up notation, right? There is no deep theorem or deep property that we showed. So let's try to prove some gradually harder and harder properties. So what is the number of total orders? What do you think is this? So total order is like sorting. So how many ways can you sort? Permutations, right? So you get factorial. Is that clear? Any questions? I mean, it makes sense only for finite S. But if you have n elements in your set, then the total orders that you can define, and all of them are valid total orders, you just do just fix the order. And you basically have to decide that, okay, what is the first element of S, what is second, what is third, what is the nth element, and that is a valid order because reflexive, antisymmetric, transitive, everything holds. Is that clear? So this is like permutations. Total orders are like permutations. For finite, for infinite, you can imagine what will happen. So let me just add for finite S. That's the claim. What else is there? Okay, yeah, this example. Let's try another order on complex. A less than equal to B if the norms are like that. Okay, we are defining this order based on the norms. Now, is it a total order? Is it a partial order? Is it an order? What do you think? Yeah, that is the problem. So I was bluffing before. This doesn't give you an order. Okay, neither partial and hence nor total. The problem is that norm of A less than equal to B and norm of B less than equal to A only says that the norms are equal. But the elements A and B are they equal or different? Well, you can just flip the sign, they are different, right? So the difference is basically in the phase of the complex number. And how many numbers are there with by changing phase? Is it finite? Yeah, so rotation is obviously infinitely many. So there are infinitely many complex numbers which have the same norm, for example, 1. So this is very far from an order. Is not antisymmetric. Example, counter example is square root of -1 and square root of -1 minus. Right, so these two are different elements, but they have the same norm. So which means that this is not a partial order even. So can you define something over complex which will be a partial order other than reals? Yeah, that's an interesting suggestion. So you have to see whether this will actually give an order, because you are comparing two things now, not a single thing. You are comparing this tuple, right? The norm comma phase. So yeah, it will be. Yes, it's a partial order. Okay. Yes, so check that. No. So the thing is, what do you give more importance, norm or phase? No, no. So norms may be in some order and phases in opposite. So how do you decide what is smaller? So you have to set your priority. I don't want to get into that. So if you're interested, check this. Okay, so there is a way to represent finite posets which is called Hassa diagram. We can represent posets as a diagram. That's called a Hassa diagram. And maybe I should say finite posets, although this is sometimes not needed, but just to be safe. So this will be, let R be a partial order. On the domain set S. So connect x, y by a line if x is less than y. Or maybe it helps to think of it as an arrow. So put the arrow head on y, maybe on the y side. So let's see examples. So using integer less than relation, what you can do is, or maybe just the positive ones, natural less than. So you have 0 which is connected by a line, right? 0 is less than 1, 1 is less than 2. This is not finite, but any finite kind of interval you can write, as you can draw this diagram. It so sounds trivial. Other example is, it may not be a, so this seems to be just a line. The thing is that it may not be a line, it may become two-dimensional in certain cases, like natural numbers with divisibility. If you define less than to be divisibility, so I think I should talk about less than equal to maybe. That's the thing. So now we are looking at natural numbers with the relationship divide, so A divides B. So what is the picture now? 0 doesn't divide anything, right? Then 1 divides everything. So start getting complicated things. And 2 divides 4. How do I even draw this? So let me say some finite. So 0, 1, 2, 3, 4, 5, 6. So the edges will be 0 doesn't divide anything, 1 divides 2, 3, 5, 4, 5, 6. 2 divides 4 and 6, and 3 divides 6. Is that fine? Right, multiples of 2 is 4 and 6, 3 is just 6. 4 is nothing, 5 is nothing, 6 is nothing. So there are also self loops, because it's reflexive, but we skip the self loops. So that was the point here. Skip loops, self loops, I mean. because that is always there for less than equal to. So that is called the Hasse diagram, and is it clear that any diagram you are given, it will define a partial order? Yeah, that is true. But yeah, so I should expand this definition. It's a good point. So what I should say here is that if x is less than y and there is nothing in the middle, there doesn't exist a z such that x is less than z is less than y. Okay, so I connect x to y only if there is nothing in the middle. So which then explains, coming back to the natural number less than equal to example, we don't connect 0 to 2 or 0 to 3 or 2 to 4 because there is something in the middle which is giving the path. Yeah, that will change this now. One and 6 and 1 and 4. Is that fine? Okay. Is this clear? So that is hopefully the correct diagram. Yeah. So now do you see that if I draw a diagram, then it will define a poset, an order? So what, how will you decide whether A is less than or equal to B from looking at the diagram? You just have to find a path from A to B. Right? If there is a path, then A is less than or equal to B. If there is no path, then they are unrelated. Right? So this is an exact characterization. It's a faithful diagram for the order. Sorry, 2 to 6? They are intersecting. What is the problem with that? The condition is that there should not be any z such that this you can deduce by transitivity. X less than z, z less than y, hence x less than y. We are trying to remove the transitivity axiom from the diagram because it is implied. Transitivity is an axiom, so we don't have to draw those extra edges. Okay, this is kind of the smallest diagram which is enough, and it's exactly enough. So let me make a statement. Let's see whether you accept this or not. Given x, there will be a unique, so actually let me write it. There is a unique y such that what do I want to say here? So for all x, if there is always a unique y such that you see the edge x to y, then what can you say about the order? No, there is, I'm looking for a property of the order. if for every x there is a unique y? Yeah, I wanted to say total order, but probably that is not true. I think only the converse is true. If R is a total order, I want to see the opposite. Suppose the relation is a total order, then for any x there will be a unique y such that x to y is an edge. Can you prove this? I can leave it as an exercise. So the hint is that you look at this divisibility diagram. So 1 is a counter example, right? 1 is connected to both 2 and 3. But the reason it's connected is because 2 and 3 are unrelated. If 2 and 3 were related, what would have happened? Yeah, so say arrow goes from 2 to 3, then 1 to 2 to 3 is a longer path, right? So you don't need to connect 1 and 3. So we see this out degree 2 only because the relation is not total, it's partial. If it's total, then you can show that this will not happen. So it means that the diagram would be what? Just the line. Yeah, so prove this as an exercise. So simple thing to prove. And this is consistent with the idea that total order is a permutation. So when you see the line, it gives an order on the elements, and the number will be size of s factorial. The ways in which you can draw this diagram is consistent with that. So your Hassa diagram removes the edges, which can be obtained from reflexivity and transitivity. Okay. And just to complete this picture, so we can define, looking at the diagram, we can define maximal and minimal elements of the poset. So when will you call an element x maximal? When out degree of x is 0 in the diagram, right? It's maximal in the poset if no element appears on top. On top of x. And when is an element minimal? Right, so the symmetric case. If no element appears below x. Right, where top and below is with respect to the edges. If there is an edge going out of x, then it's not maximal. If there is an edge going in x, then it's not minimal. Is that clear? Now, are these unique? Are maximal or minimal elements unique? What is an example? Correct. Or yeah, minimal you can see 0 and 1. Right? 0 is both maximal, minimal. 1, sorry. There is no out degree is 0, in degree is 0. Oh, yeah, there is one problem. There is an edge missing. All the numbers divide 0. Should I draw that? We should not draw that. I think we should. Yeah, let's just remove 0 then. If it's too confusing, let's remove it from the set. So now 1 is minimal. Is there something else minimal? Yeah, so it makes sense that in divisibility relation, nothing can be minimal than 1, right? Because 1 divides everything. And the bigger numbers you get in your finite picture, those will be the maximal ones, like 6, 5, 4, and so on. So they are not unique. So now we can move to some harder properties that will come with chains and anti-chains. So what is a chain in a poset? So chain will basically be the lines you see in the Hassa diagram, right? Like line meaning in general like this 1 to 2 to 4 or 1 to 2 to 6, 1 to 3 to 6. So these are lines. So these are chains. So chain C is a subset of the domain such that what is the property that defines it? This 1, 3, 6, what is happening there? Any two elements are comparable, right? It's kind of in the local world, it's a total order. So such that any two elements are comparable. That's a chain. What's an anti-chain? So anti-chain A is a subset of S such that, so let's see the example first. Anti-chain will be, yeah, 2 and 5 or 3 and 4. The property is that no pair of elements are comparable. That's an anti-chain. Such that no two elements in A compare. Obviously, when I say two, I always mean distinct. Otherwise, it's reflexive is a counterexample. So no two different elements are comparable. Any pair of distinct elements are incomparable. That's an anti-chain. So what is the longest chain in the power set? Power set with elements 1 to n, relationship is containment. What do you think is the longest chain that you can find? the first element you can take, for example, 1, next will be 1 comma 2, then 1 comma 2 comma 3, right? So an example chain is you take 1 singleton, then doubleton, then tripleton. Yeah, good point. We should respect the emptiness also. Okay. Yeah, so the longest chain you can find is n plus 1. That's the answer. Can you find anything longer than this? Is this the longest? Right, so prove this as an exercise that this is the longest. Longest is n plus 1. You can't have more than that. So that's about chain, longest chain. What do you think is the longest anti-chain? That is when things become interesting. Okay, so what is the longest anti-chain in the power set? So you have to find maximum number of subsets such that no two compare. Sorry? So the size will be? No, I can give you exponentially many subsets. So what I will do is, suppose n is 100, you take the look at the collection of all 50 sized subsets. I claim that they are all incomparable. Is that fair? Yes, there is a lot of, the longest anti-chain is very, very large. Now the question is there something larger? Right, that is the fun question. So example of an anti-chain is all subsets of size n by 2 floor, in case n is odd, form an anti-chain. And all subsets of size ceiling, that's also an anti-chain, both are equal in size. N choose n by 2 floor. Right, so this is very close to 2 raised to n. This is a lot of subsets that you are getting, very different from chain. Any questions here? Now we want to show that you cannot do better than this, and in fact these are the only longest anti-chains. So this is called Sperner's theorem. He proved it in 1928. Okay, so very old. But the proof is not trivial. It's very tricky. Or maybe I shouldn't have said that. You find a simple proof. How do you think you will show this? So the theorem says that longest anti-chain is only one of these. So in particular, it means that for even n, it's unique. Okay, so if you take n to be 100, then the longest anti-chain is a unique subset, a unique collection of subsets, and this is exactly collect all 50 sized subsets. And if n is 101, then you can do it in two ways. So you can either collect how many? 101 by 2 floor, right? So that's 50 or 51. So you can either, 101, right? So for 101, you can either take 50 or 51. Two anti-chains will be obtained, and you may think that why is it not possible to merge the two or pick some from one, some subsets from other? You have to show that those things are not possible. It will not give you the longest anti-chain. Okay, this cannot be improved. So how do you prove such a thing? Any ideas? So we'll actually prove some relationship between chains and anti-chains. Okay, we'll develop some theory and then this result will follow. So define a maximal chain we'll call it M chain to be it starts from empty set, goes to the end, and in the middle you can have you have many options. Right, so sizes are respectively 0, 1, 2, n minus 1, n. So the begin and end sets are fixed and everything else you can change. So how many maximal chains are there? That we have seen before, right? Number of M chains is, yeah, that's just n factorial as before. So let's remember that. Now consider the longest anti-chain. Let A be, in fact, any anti-chain. If you take a M chain C, let's call this C here. So how many elements of the chain can be in the anti-chain? At most one, right? Because if two elements, let's say Si and some Sj, both are in the anti-chain, then they will be related. So per M chain, there is at most one element in the anti-chain. Let's record that. So C intersection A is less than equal to 1. So less than equal to 1 element of C in an anti-chain. Next I want is let's count the number of M chains containing a set S. This is size k, let's say. So how many maximal chains are there containing a subset? K is just the size of S. So I want a function in terms of n and k. That is what I want. What is it? Yeah, so why? Mm-hmm. And you can't interleave them, S with S complement. No, I don't know. So, but yeah, your answer is correct. Um, so what we are saying is that one of these is S, right? So the chain that we are interested in is there is this S0 fixed, and there is Sn fixed, and there is an S somewhere in the middle. Right, that so this is one element, that one set that you have fixed. So now actually the position is also fixed, the set elements are also fixed. So all you can change is what comes before S and what comes after S, right? So what comes before S, that is essentially in bijection with, as was pointed out, permutations on k elements, k factorial. And what comes after, there are these n minus k elements, how you permute, that will exactly define the sets that come after. So that's n minus k factorial. So that is the count. So number of m chains with S is equal to k factorial times n minus k factorial. How does it change as you vary k from 1 to n, this function? Right, so you show as an exercise that this is least at the midpoint. So this is always at least n by 2 floor times n by 2 ceiling factorial. Is that clear? This you can show easily. Okay, let me stop because this proof is long. Any questions you can ask?